NASA had just released a probe in the direction of an object 100 times larger than any interstellar mass hurtling through our solar system. What started out as a scientific intercept became a jaw-dropping discovery. This wasn't just a rock. It moved, reacted, and left behind something impossible. What the probe discovered changed everything. The moment they decided to act. NASA's ambitious move. If you find stories like this captivating, make sure to subscribe so you never miss the latest discoveries and missions. It started the way these things always do, quietly. A single point of light, moving only a little too fast, carved its path across 3 consecutive sky frames. What seemed like a flicker became a flag. Astronomers marked the anomaly from survey data pouring in from Pan-STARRS and the Vera Rubin Observatory, then passed it to NASA's Minor Planet Center. Within 36 hours, X100 had an initial designation and a problem. The object was coming in fast, much faster than any asteroid in the catalog. Its trajectory was hyperbolic, on an open-ended route through the solar system, like Oumuamua and Atlas before it. But this one wasn't a pebble, it was a mountain. Estimates based on reflected light and Doppler flow suggested something at least 100 times larger than Atlas, with a radius likely exceeding 2 kilometers. That put it well beyond the observational comfort zone. "We've never had an object this big coming in this fast from outside the system," said Dr. Ana Avos, head of NASA's Planetary Defense Coordination Office. It wasn't just an opportunity, it was a test. The decision point came within a week. Orbital Solutions gave NASA a shrinking window, only 58 days, to mount any form of intercept. Observation alone wouldn't be enough. If it passed by and left, the secrets it carried would vanish with it. So the decision was made. For the first time in history, humanity would try to intercept a massive interstellar object before it left our reach. The mission wouldn't just observe. It would attempt to get within 1,000 kilometers and send back high-resolution data no telescope could ever match. A probe would be launched fast and lean, built to chase something that wasn't waiting around. Sometimes, one mission planner said, you don't get to ask the universe for a second chance. But the size of X100 wasn't the only reason to act. It was the way it moved, and what it might be made of that made it a potential threat. And that leads to a deeper question. What exactly was X100? The closer scientists looked, the stranger it became. At first, the idea was simple, a large comet from another star system. But everything about X100 pushed back against expectations. Its mass was enormous, with a density suggesting something more solid than typical icy bodies, not a loose rubble pile, but more like metal or stone. And yet, it glowed. Spectroscopic surveys revealed signs of outgassing jets of gas, possibly carbon monoxide and cyanides,
bursting from vents as it neared the sun. It was active, but not like a normal comet. The coma didn't behave predictably. The tail curved in reverse. Some emissions appeared in unusual spectra, hinting at compounds unseen in any known comet. More disturbing were the fragmentation models. If the object cracked under thermal stress, it wouldn't crumble, it would shatter into high-velocity fragments, each potentially catastrophic in a collision with satellites or future missions. This wasn't just about learning, warned project analyst Xiao Jin. This was about preparing. If one of these gets captured by gravity in a future pass, we'd better know what we're dealing with. Then there was its trajectory, a perfect inbound vector toward the plane of the ecliptic. Retrograde? Not just rare, statistically unnatural. Some theorized that X100 was ejected from a failed star system, perhaps an ancient planet tossed free by a supernova. Others pointed to its acceleration profile, small but measurable, the same mysterious drift that made Oumuamua so famous. Is it natural? Possibly. Is it simple? Definitely not. We're not saying it's artificial, one analyst said, but we can't say it's not either. And so the next step became even more urgent. If X100 held secrets, it was time to go get them. Reaching X100 wouldn't be like chasing a moon or circling an asteroid. It was flying by at over 80 kilometers per second on a one-way escape trajectory. There would be no second pass, no orbital insertion, only one chance. NASA had only a few viable systems ready to adapt. After heated internal debate, they greenlit a modified version of the Draco-class interceptor. Originally designed for planetary defense tests, it would launch on a Falcon Heavy stripped down for speed, carrying a compact spectrometer, high-resolution imaging arrays, and a radiation-shielded data core. No sample return, only a flyby and a flood of data. The mission would need to leave Earth orbit within 29 days. That meant skipping traditional planning cycles. Engineers raced to reprogram the autonomous guidance systems, factoring in the object's high-speed trajectory and gravitational mechanics. To reach X-100, the probe would swing past the Moon for a gravity assist, then accelerate on a hyperbolic burn. Delta V was everything. The probe needed a precise velocity increase to match trajectories, not slow enough to fall behind, not fast enough to overshoot. Any deviation of just 0.1% in vector velocity could miss the intercept window by tens of thousands of kilometers. "We're threading a cosmic needle at 80,000 miles an hour," said lead navigator Emma Kulik. "It's not a challenge, it's a slingshot with one bullet." Communications would be limited to brief bursts through the deep space network with multi-minute lags. The probe would need to think for itself, entering autonomous intercept mode 48 hours before closest approach. No corrections allowed after that.